This is our lab number 5. After installation of the WSL, then we will run the command prompt from administrator account, and when we will run the command of WSL, then it will show that there is no currently subsystem as we haven't installed the distribution yet. And it will also tell to us that by using this command, you can check all the distributions that are available, distributions I'm talking about that you want to do. You will install by this command. In our case, we have downloaded Ubuntu. I've written the command install Ubuntu. The first it will going to be download, then it will going to install. After installation, it will tell to you that create a user account. The direction of that account is it shouldn't be capital. These are the restrictions it will show to you whenever you are doing something wrong. And then I've created SIMD_test account. And then after that, you will type the password and then retype the password. And then you will get successful account. You can verify this account as well if you will open the Ubuntu from application. Then it will start working over here. If you will type the command sudo apt install and then we'll enter our password. Then you are viewing that successfully command have been executed. After that, the initial requirement of the Ubuntu can be installed by this command that I'm writing, specifically to build the essential parts of the Ubuntu. As soon as I'll click enter, you can see that initially required things for the Ubuntu are getting installed. That would be useful in your programs, specifically for compilers. So it will install all the required framework by default. And you are viewing here E showing the error for those that are not successfully installed over here, while the rest you are viewing have been successfully installed. Okay students, now if we will open the Ubuntu one, then we will check that whether G++ is installed or not. So we will write G++ --version over here, and when it will show a display like this, then it's good. It represents that we have this installed. In case if it's not present, then we have to run two commands. First command is sudo apt-get update. That will install the remaining packages. In my case, I have already installed this. After that, we will do sudo apt install G++, which will install G++. I've already done this step as well. After that, when I'll write this command, it will show to me. I've already done and already showed to you all. After that, we will make a folder for VS Code. I've given the name it as SIMD_lab with mkdir, that is making directory. After that, we'll go inside that folder and then we'll type code space dot. Then it will open the VS Code. And as soon as VS Code will open, we'll do the first task. We will search WSL over here first. And if it's not installed, I recommend that you need to install it first. After this, we have generated a single program, simd.c++. In this program, we are doing what? We will compare serial addition and vector addition. So we have included the three headers. We have used the standard namespace for C++. Here we have a main function where we are taking two arguments, argument C and argument V. At the end, we are printing two things. That is our standard loop that is running serially, how much time taken by that loop, and our vector loop, how being time taken by that vector loop. For that, at the start, we have taken a size variable for our arrays, and we have two arrays over here to which we will add to each other. Then we have a start variable which tells the starting time, where we will store the starting time before execution. We have two variables, duration and vector duration. Duration is for normal addition, that is serial addition, and vector duration is for vector addition. Then we have two arrays over here, A and B, and we have fixed the size as 512. You can see above. After that, we will initialize these arrays. The loop will run from 0 to 511. So now in A, we will multiply with 1 to I plus 1. This will make the array of this format. And in B, we will multiply with 2.5. So we will get the array of this type. After that, we will see the logic of standard scalar loop timing, for which we have taken a start variable. We have taken a clock time in this variable and a total variable, a float starting with 0 is here. After that, to check how much time would going to be consumed, we have set the number of iterations 100,000 so that we can get a proper estimate. As we all know that the float instructions by default are quicker. So if we will set its size smaller, it will give us almost 0 seconds. Here we have applied a small loop where we are actually finalizing and calculating the total and storing it. This will reach to 512 and then it will go into next iteration. Total will again 0 and then again it will become 512. So basically 100,000 times the above loop will run and the inner loop will iterate for every variable. So it will run 512 times. From this we can get a good amount of duration on which the calculation can be performed. After the loop, we can calculate the duration over here. We will subtract the start from the current clock and will divide with the clock per second. This is a double variable. It will give the answer in seconds. Here we have the same concept of vectorized loop, to which we are calling it as OpenMP SIMD. SIMD is basically single instruction multiple data stream. Obviously you will study this in theory classes, that tells CPU that a single operation on multiple data in parallel can easily be performed rather than to give serially each operation to each data. So obviously it will run in parallel and it would be faster. It will group the vectors and will perform the instruction. For example, in this case we are adding the numbers. Same work we have done over here as well. For start we have taken a clock, which was our starting time. Then we made a vector total variable. We have the similar loop concept again. 100,000 times it will run. But here, rather than the normal for loop that we have taken above, we have taken pragma OMT SIMD for loop that will treat them as a vectors and will perform the calculation in parallel. To remember where we use pragma OMP parallel, that actually assign the task to the threads. For example, if there are 10 iterations, so 5 iterations would be given to one thread, 5 would be given to another thread. Its work is all the iterations, it will run in parallel via multiple threads. This is the basic difference of these two commands. As soon as this loop will complete, we will calculate the vector duration. This is the same task that we have done previously. Answer will come in seconds. After that, by using the cout command, we will display the output. Now we will run the code. We will now similarly first compile the code. G++ simd.c++, which was the name of our program, and we have -03, which will tells to our compiler that this program contains SIMD instructions, and -03 basically which used to optimize the SIMD instructions. If we will not use this, then serial and vector time could come equal because it will not going to use these optimizations. So this is a special flag that we normally use with SIMD. Otherwise, it does not require. -f OpenMP we have already used in the previous sessions as well to represent that we are working in OpenMP. -o executable is with the name SIMD, which will make the SIMD executable file. Now we will run this. It will going to run, but initially it will take time to display over here as we are running this on the virtual machine. So it takes time to update. But if we will just directly run this, the code will run that we have run the simd.exe file. So here we are having two outputs. As right now my processor is currently idle as it's not doing any complex task, as no heavy task is being performed. So serial and parallel execution results are almost similar. But it depends on the computer. You are viewing 0.035. I've also tried this on a busy machine. It has represented my output for standard loop. It was 0.45 seconds, and for vectorized loop it was 0.12 seconds. So it depends on your machine. Currently both the instructions run fastly, almost in milliseconds. So basically the purpose of this code is to explain the SIMD. Okay students, The results that we have taken out previously were almost similar. There are two reasons of that. One is that your processor is working very fast and performing the instructions by any means quickly. That's why you are not viewing any difference. Just like here, 0.001 difference. So to handle this, we will do just one extra work, because our extra addition calculation, that is running in parallel. But this vector total, that is calculating the actual total, that is not the part of the parallel execution. So what's happening over here, for example, if it's going for 100 additions at a time or doing 100 calculations at a time, these 100 calculations are the part of the result. But to add on this total, it takes time, due to which at the end of the day, the standard loop and the vectorized loop are giving the same answer. Even though this thing is calculating quickly, but at the last addition is taking time. So in previous labs, we have already studied the clause reduction, in which we will place a variable, total, and the operation that we are performing, that is of addition. So that's why we have written plus over here. What will happen, whatever the value will calculate, it will store into the memory in one place, and as soon as this whole loop will end, it will add the total over here. This will just generate a minus overhead, but after adding this part in the code, we can see the difference of standard and vectorized. And if we will again recompile and then we'll execute it, now we can see that now the standard loop time is more, total is similar, and the vectored loop time is 0.008 seconds. It has noticeably decreased because it's now properly working in parallel. Total of both the executions is same, as the logic was implemented the similar. Only one addition code have been applied, that is reduction, and we got our appropriate result. Okay students,